fitness, selection, and population management. So we already know what these things are, right? Fitness, well, that's like the goodness of a candidate solution. Selection, that's how we decide who we pick to be parents or who gets to go to the next generation, whatever. And then population management. How are we going to how are we managing our population? In the example I did with TSP, it was a very simple way. It was just population is a fixed size of 100 or something. And based on how selection works, that's, we fill up that population, and once it's full, we do the next generation. But there are other strategies that are common-ish. And really, remember, everything that we're looking at is just one of an infinite number of possible ideas. So we'll talk about these things, but the point here is be creative, right? Like, we can talk about some ideas here, and yeah, they're common, but when you're working on an assignment or working on a project, get creative. That's where you'll learn more. That's where you can have more interesting results, have fun. That's where it is. Last lecture was about crossover, like the genetic operators, right? And the encodings that, we talked about the encodings and genetic operators that kind of fit well with certain encodings. We talked about like binary, regular integer, floating point numbers, and then like permutations of unique numbers. So now we can talk a little bit about other aspects. And you know what? To give a little bit more of a sense of the other things I'm going to talk about, and some of these lectures are fairly large, is we'll do this, but then later I'm going to spend some time talking about genetic programming and also particle swarm optimization. We'll talk a little bit about parameter tuning, multi-objective, but soon at one point I'm going to need to show you how we effectively compare results between your algorithm and their algorithm. How we want to do that the right way. Because, at this stage you might think well, I got a better result than him, therefore, my algorithm's better. Well, no, all we can say is that you got a better result, but was that just by dumb luck because everything's stochastic? Or is it because, your algorithm is just always outperforming their algorithm? And we have good ways to check that. Some fairly standard strategies. And some of you might remember them from statistics class or something. Raise your hand if you've heard of t-test before. Yeah, of course you have, right? How about a Mann-Whitney U-test? One. It's kind of like a t-test, but better. The problem with a t-test is it assumes that your data is normally distributed. It assumes that it's got a nice bell curve, Where Mann-Whitney U doesn't make that assumption. Yeah.
So if we're comparing, say, we had a bunch of different algorithms and we had more than 3, would it then become a case of not using a t-test, but using an ANOVA test?
Yep. But still, there are other strategies for doing a big comparison. The trouble is, once you start having multiple things you want to compare, well, if I have 2, I need to make one comparison. If I have 3, I got to do that comparison, and that comparison. And it starts to grow exponentially, right? So you end up having this combinatorial explosion of comparisons, which becomes problematic. Anyways. And that can get really frustrating, especially in the realm of evolutionary computation, because there's a lot of tunable parameters here. We have things like your population size, your number of generations, your mutation, your crossover, those are the things you're probably thinking of. Maybe selection size. But other things that we can change out are, representations, what the fitness metric is, what crossover we're using, what mutation we're using. There are a lot of changeable things. So if you start making all these changes and you want to do all those comparisons, don't go crazy, because that will make you go crazy. But the t-test is kind of like a quick and dirty way of doing a comparison of distributions to tell us if 2 distributions of results are different. I'll give you a quick primer. because this might be helpful for assignment 1 if you want to do some statistics. Let's say, for example, let's say I'm doing TSP, right? I could, shoot, do I have, I do not. If I'm doing TSP, and I hit run once, right? And on some instance, some problem instance, TSP instance X, you hit run, and we want to minimize. This is 0, that, towards infinity. And you hit run, and you get your best result in your population comes out at the value of 1,237. That's just some arbitrary value, okay? Can you see that reasonably well at the back? Yeah? All right. And then someone else comes along and they hit run, and you see 1,621. Right? Which is better? This one, right? Like that's a silly question. Which one is better? Well, clearly, this one is a better number than that, and if I'm minimizing, I want that result. But that's when I hit run once. And these are stochastic things. These are things that every time I hit run, I'm going to get a slightly different result, right? So if I hit run again, maybe the next time I hit run and get a value like here. And then run again, and maybe it's here, and then here, and then here, and then here, 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 here. And they're hitting run, and they're getting values that are, around here. We're going to start getting distribution. So we'll create a histogram. And be honest. Raise your hand if you don't know what a histogram is. Because if you don't, that's fine. Okay, a couple people. So, all it is, you probably do know what it is, you just haven't really thought of it. If I hit run, let's say I'm doing a histogram of some discrete values. Rolling 2 dice. Dice. Right? So, let's say, for an example, I roll 2 dice. And there's a limited number of unique values I can get. Right? I have, the minimum number I can get is 2. And then we can have a 3. Right? We can get 2 with a 1 and a 1. We can get 3 with a 1 and a 2, or a 2 and a 3. We can get 4 with a 1 and a 3, a 2 and a 2, a 3 and a 1, right? And so on, all the way up to 12, right? 6 and 6. So 4, 5, 6, 7, 8, 9, 10, 11. 11, 10, 9, 8, 7, 6, 5, great. So each of these ticks is going to represent something. So I'm going to hit run. I'm going to roll my dice and look at which one, what number I get. Maybe I get a 5. I'm just going to make like a tick there. And you know what? I can have like a y-axis here. And this will be like count. Then I'm going to roll it again. Well, this time I get a 6. Roll it again. Oh, I got another 5. Roll it again. I got a 9. Roll it again. I got a 7. I got another 7. I got a 2. I got a 7. I got an 11. And I'm just going to keep doing this over and over and over and over and over and over and over. And we're going to get a distribution that looks something like this over time. Right? Whatever the counts are don't really matter here. It's just kind of like what's relative. We're going to get a distribution that looks something like this. So 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Pretend those are the same values. And these kind of like like bars, okay? Just pretend these line up. Right? So, there we go. This is my distribution of rolls. I'm going to roll the dice. I'm going to run once. Rolling the dice is a run. And I'm going to look at the results, and I'm going to record it. I'm going to roll the dice again, record it. I'm going to keep track of all of those. And for fun, let's just do like... images. It'll look something like this, right? Or here, maybe that's a little nicer. Because the reason it looks like this is because based on the possible, like the number of combinations of dice and like what they could come up as, there's only one combination that gives me 2. And there's only one combination that gives me 12. But there's a lot of combinations that give me 7. I can have 1 and 6, 6 and 1, 2 and 5, 5 and 2, 3 and 4, 4 and 3. There's a lot more possible combinations there. So that's why the distribution looks like this in this scenario. But you could try this. You could take 2 dice, start rolling it, count every time you get the different number, plot it on the axis of like, well, these are the possible values, and this is the frequency that that number came up, the count. That's the distribution. Now this is very blocky because they're like discrete values. If it's a continuous thing, it would probably look something more like this, right? Now with TSP, for example, it's still discrete, but the number of possible values is a hell of a lot more than 12, right? Because like, well, when the problem instances get large, there's a lot of possible different distances that you can get. And maybe they're real numbers, but they're still going to be like unique within the problem set, because there still is a finite, well, not unique, but there is a finite set of those values. So with TSP, and I'm going to talk about an idealized scenario. I really wish there was an eraser in here and not whatever this is, a nub. Hey, it actually works pretty well. So, I've got this. This is 0. This is towards infinity. I don't know. If I hit run, and I keep doing that, I keep rolling the dice, I keep hitting run on my GA, and I keep track of all of the best values that I see for each run. I could do it a little differently, right? Because if I have a population size of 100, maybe I keep track of like all of the 100 or maybe the top 10, but whatever. I'm just going to take the best one each time I hit run, okay? If I do that, I'll get a distribution that might look something like this, okay? And as I keep hitting run over and over and over and over and over again, that's going to like fill in hopefully reasonably nicely. This is not to suggest that your distribution might not be normal. This is like a normal distribution. But if I get a distribution like that, there's a number of metrics I could take of this. I can calculate the mean, right? Take the average, calculate the standard deviation, you know, variance, all these different statistics, right? And then your buddy comes along and has a distribution that looks like this. All right? So green's not doing too well. Switch to red, I guess. Let's try this again. If you look at their average, and you look at your average, like, our average is better because it's more this way. But the trouble here is, in this scenario, you know, we could visually look at those distributions. The distribution is the shape of that, like, you know, curve. I can look at those distributions and say, you know, they look pretty different. It looks like ours are better. But a lot of times things won't be that nice. Things might look something like this. Right? Now, look, my average is going to be probably better than the red one. Blue's better than red. Probably, right? Based on how that looks. But based on our observations here, sure, the mean looks better, but is my algorithm actually generating better results than theirs? Is blue really better? Because the next time I hit run for blue, I don't know, if I keep hitting run, maybe it starts to change shape a little bit, I don't know. So what we care about is, okay, great, the mean is better, that's wonderful. But can I say for certain that the two things that I'm observing, the two boxes, the two random variables, in this case, my GA and their GA, blue's GA and red's GA, can I truly say that I am actually observing things that really are different? Because it could be possible that I just get kind of like unlucky, and maybe I don't realize this, but my friend copied my GA entirely, exactly. And it just so happened I hit run 100 on mine, and I hit run 100 on theirs, and this is what my distribution looked like, and this is what their distribution looked like. So is this difference meaningful? So you're shaking your head no, but you know, I don't know. I don't know, but we can calculate this. Just one sec. We can do a calculation here to try to tell us is there a difference here? So t-test is an example of one way to do this comparison. And when you run a t-test, what's the output of your t-test? What do we call it? A p-value. Who knows what the p stands for? Maybe it's Greek letter, but I always thought it was a probability, like p-value, probability value. Someone Google it. See if it's right. You're nodding yes. Is it probability value? Haha. So, probability value. What that tells you, okay, raise your hand if you've ever heard the less than 5%, so it's significant. All right, well, I got some funny news for you. That number is arbitrary. Because what the p-value tells you is what is the probability of not the null hypothesis. And the null hypothesis will be like, okay, we'll assume they're the same. We're going to assume that there are actually no difference here. That's our starting position. And if I calculate a p-value of 0.17, that tells me, there's a 17% chance that they are the same. There's a 17% chance for that null hypothesis. And you might say, well, that's pretty good, right? And if I get a p-value of exactly 0.05, so there's that 5%, there's that threshold, so I can say significant. And that means there's a 5% chance that they are the same. So because I get to go, I got better than that 5%, I get to say, oh, there is a significant difference, assuming an alpha of 0.05. That's like the significant threshold. So if I have 5%, there's a 5% chance that these numbers are the same. If it's 0.049999, just better, it's significant. So I can conclude there's a significant difference, right? It's less than 5%, therefore these distributions are different. Here's where lazy stats becomes a problem. What do these things mean? It doesn't mean that therefore these distributions are different. It means that there is a 4.9999% chance that they're different. or that they are the same. So that also means that 1 in 20 times, I will actually have things that are the same. Because if it's a 5% chance, and I do 20 different experiments, chances are, one of them, the conclusion I made because of 5%, one of them, where I say they're different, that was just by chance they came up as different, when in reality they weren't. So what a p-value tells you is the likelihood that the two things that you're comparing are the same. It's not this mystical number that you just need, 0.05, that's what I care about. No, that's lazy. What it is what is the likelihood that they're the same? And if you say 5%, well, that's pretty good. But if you do a p-value calculation and you get like 1.7 times 10 to the negative 29, okay, now we're talking. Now we're talking, these things are definitely different. Or, well, good luck. You know, I guess it's possible that they're the same. A 1 in times 10 to the 40, whatever, or negative 4, whatever. So that's what the p-value means. So when you are doing your tests, and the good news is if you're doing it in you don't even need to build your GA in Python, but you can do your statistics in Python, which will be easy peasy. Open up SciPy and you're great. NumPy, SciPy, well, I don't remember where they are. SciPy.stats, I think, is where all the good stuff is. So you can do your t-test, your student's t-test. That's what it's called. And it will tell you, it'll give you a p-value, and it'll also give you another number too that I can't quite remember, but it'll give you a p-value, and if you see something like 0.10 of a comparison, that's not necessarily a bad thing. That just tells you, oh, there's a 10% chance they're the same. That gives me context of a reader of your work. This 0.05, it's just arbitrary. Does anyone know the story of where the t-test came from? It came from the Guinness Brewery. So, an interesting thing here, I will say, is the t-test is a nice and easy formula, relatively speaking. It's a nice and easy formula for doing this comparison. But there are limitations to what the t-test tells you. It assumes that they're normally distributed, when in reality, a lot of things might not come out normally distributed. A Mann-Whitney U-test is another way to get like a p-value, but it doesn't have to assume, and the Mann-Whitney U-test is actually more of like an algorithm than like a little equation. But really, what you want to do, the really good way to do it, and I'm not going to recommend you do this for this assignment, but the right thing to do is what you call a permutation test. And I will talk about the permutation test a little bit later. Or maybe I should just do it now. Get out of the way. Yeah?
So I've heard about it before, but I don't really understand why it's such a faux pas, like p-hacking.
P-hacking, why it's such a faux pas. So, if I hit run, so p-hacking is, raise your hand if you've heard of the phrase p-hacking before. A couple of people. So there's this phrase called p-hacking. And this is where scientists are being very unethical and trying to cheat. And I'll give some context of why they might feel the need to do this. For better or worse, the way the academic system works for researchers, and we're not talking about private industry, we're talking about universities, academia. Now, it might be the case that a lot of people don't know this, like, my job is scientist who teaches, right? I'm not a, professor, I do research. That's like my job. But I also teach you, but I do research on things. And in order to be successful in order to get tenure, in order to get more funding, in order to get, to get a good reputation and whatnot, I need to publish papers. And the problem is, if I want to publish papers, I want to publish papers in good places, in good venues, like maybe a really well-respected journal. So if I have something like in my area, if I publish in IEEE Transactions on Evolutionary Computation, woo, that's good. If I publish in Bob's Fun Science Journal, that's not good. Okay, so there is like a hierarchy. It gets fuzzy because, well, it depends on how broad and narrow their area is. But there's science and nature. That's like very broad, and if you publish there, you're set for life. So I need to publish, but the problem is these places don't like publishing negative results. They don't like to publish things that aren't significant. So if your p-value is 0.057, I'm sorry. Because we're so obsessed with that arbitrary 5%. But on top of that, they don't publish negative results. Which to me is kind of disappointing because negative results are interesting. Negative results are the fruit of all the research you did. You could spend a year working on something, and at the end of the day, you're like, oh, it's 0.06. Well, I guess I wasted my time. Well, no. That's still interesting. It's still meaningful. Maybe you come back and your p-value is like 50%. Well, that's not very, I would never make any grand conclusions on something like that, except for, oh, I guess my idea wasn't that good after all. Here, read this if you want to learn how not to do something. Which might be valuable because someone else comes along and says, I've got this great idea. And it ends up being a terrible idea they dedicate a month of their life to. But they would have found out if the bad results were published somewhere. So it's actually becoming a thing where articles, like there's journals for like bad results. There is a unofficial journal, I think it's like University of Ottawa, and the journal's called like Journal of Terrible but Interesting Results, right? You can just push the results there, it's fun. So I am incentivized because if I don't get publications and then I apply for grants, and grants is how I can do my research, right? I hire graduate students. They cost a lot of money. So I have to get grants to get money to pay them to do research too. So it gets really expensive. I need grants, but if I don't get publications, I'm not getting grants. And if I don't get grants, So I have a lot of incentives to cheat. The system is set up in such a way where we've got perverse incentives. So, and by the way, I realize this is off topic from evolutionary computation, but hopefully this is, you find this meaningful because there's a lot of context in the greater university world with this rant. Yeah, cool. So there's all these perverse incentives. So the problem is, I can do p-hacking. There are a bunch of ways to do p-hacking, but here's an example of what it would be. If I roll my dice a bunch of times, and you roll your dice a bunch of times, and I want to calculate, are they different? Maybe they're weighted differently, right? And I really want to show that they're weighted differently. If I roll the dice 100 times, and then the other one's 100 times, and I compare the distributions, and I get a p-value of 0.09. Shoot, that's not what I wanted. You know what? Let's just do it again. I'm going to roll those dice 100 more times. Those 100 more times. I calculate the p-value. The p-value comes out to 0.10. Crap. All right, I'll do it again. Comes out as 0.06. Oh, hey, I got lucky that time. Because these are there's a lot of randomness involved, right? I keep doing it. I just keep doing it over and over and over, and finally I get a p-value of 0.049. I just got really lucky on those rolls. And now I go, haha, I'm going to stop now. Because I showed what I wanted to show. When in reality, I didn't roll those dice 100 times and 100 times. I rolled it 100 times plus every other time I did it before. And if I were to observe all of those things, p-value might not come out to something less than 0.05. So I can cheat like that. And there's like a famous plot you can see of like psychology. Neuroscience and psychology is known to be the most notorious for unethical results. See if I can find the plot. No p-value. No.
Oh, there, down there, the WordPress article. It has like, it's red and black.
This one?
No, I don't think, it's that one. Yeah, that, I think.
Yeah, that's not the one I had in mind, but I can kind of show what it looks like. There is a famous plot that I can't find right now. That if you go look at all of the things in the literature, if you go read like a bajillion papers from some scientific field, and you keep track of all the p-values. So I'm going to plot the distribution of p-values. And if you do that, you know, maybe your plot looks something, and here's that like 0.05 mark, 0.05. And a lot of times we want the numbers to be less than or sometimes greater than, because sometimes I want to show that two things aren't different, right? So what I can see a bunch of times is, oh man, green is terrible. You might see something like this. Where, oh, magically, as you get like closer and closer, the p-values, basically, this is where you know people are cheating. Because they're like, my results aren't there. Try again, try again, try again, try again. Oh, there we got it. So there's like, you see that, you go, wow, scientists are being bad. That's bad. Because, and what makes it bad is this is like science, right? Like if I read someone's paper to learn something, and it's actually full of shit, but I use that to solve my problem, I'm in big trouble, right? It's like a domino effect too. Like the bullshit that they come up with, maybe I use it, and I get terrible results, but the results are going to be that much more worse because of what they, you know. So that's p-hacking. Whoop. Yeah, so that's an example of it. There's other ways you can do it. I mean, if I run it a bunch of times, maybe I just pick the ones that I like. Anyways, so hopefully that answers your question about p-hacking. Yeah, so watch out for that. What time is it? 57, shoot. All right. Any questions before anything? Yeah.
Can I ask what the assignment one will be modification should I do?
Sorry, say that again?
The modification. What should I do for the modification?
Whatever you want. It doesn't matter. Like, this is where I want your creativity. This is where I want you to go like, you know what might be a fun idea? If I do crossover this way, you know, like and it's brand new or something. Just do whatever you want. I want you to be creative. And it doesn't even matter if what you do is really dumb in the end. Like if you're like, I made this change and the results got terrible. Fantastic. You had your hand?
So what's the difference between like a mod and just doing something differently than the way you had it?
I would say that's, at this stage, that's hairy because you haven't really learned about some of the standard modifications yet. For example, here's a freebie, okay? Here is a freebie modification that I'll show you in the next 7 minutes. It's something called elitism. No. Okay, so what I'm going to do is, so elitism. This is the easiest modification you could do that almost everyone does these days. So you should do it. And if you do this, you'll get a point for free. You take, So based on how this is written, I just randomly pick, right, all the time. Elitism is, well, but I'm also going to guarantee that the top X always make it to the next generation as well. Typically what I would do is only the top one. If you start to do like 2, 3, 4, you'll converge way too quickly. So an easy way to add this to my thing here is I'm going to be really lazy and do it a super lazy way. All right, so I made the population size an odd number. I will find argmax. So new. And then I do new population dot append. Perfect. So I can do new population dot copy chromosome population at index np dot argmax of fitness. There. I did this all in one line of code. I probably wouldn't do it if I wasn't trying to do it in less than 5 minutes. But what am I doing here? For those of you not that familiar with Python, np argmax is, np max tells you what the max value is. np argmax, np is for numpy. Oh yeah, you got a question?
Well, I thought you were asking how we got it.
Oh, okay. NP argmax is the index of the top fitness, right? So I find the index of the top fitness. That corresponds to the chromosome at that index. I make a copy of it, and it automatically is allowed to go to the new population. Great. And then I do range, population size 2, yeah, whatever. Population size by 2. Is that right? We should start at 1, but it wouldn't matter. Okay, great. And now with elitism, this tends to improve results by quite a bit. You do this, look at that. 1 extra point. Huzzah, right? See if I can run it real quick. I wouldn't be surprised, like, don't be mad at me if it doesn't work because I'm doing it. Never code in front of people, right? Yeah, what's up?
Say you wanted to do your stats in something that's more like stats oriented, like R. Would it be a pain in the ass for TAs to have 2 different languages, 2 different files?
No, it won't matter because I don't even really care about the code you use to generate your stats. You just care about your stats.
Oh,
Yeah. All right. Well, there's the best. Well, okay. So there it is with elitism. Now let's go back and see. Okay, this is a really small example, so I might not impress you that much. But let's see what happens if I copy out elitism and run it again. No, crap. So the last time the plot was like pretty abruptly to the best. See what happens here. Well, all right, fine. The instances were too small. But if I made these problems harder, this would help a lot. I recommend it for TSP. It'll be really good. Anyways, see you. Oh, guys, I have some amazing news. Only about